Hello and welcome to this video AI session on column buckling. In this video we will solve the example problem shown on the page. However, I want to warn you that you won't find this example problem in your textbook, so from time to time you may want to pause this video and take some notes. Let's begin by reading the problem. We have an aluminum column which is fixed at its base and braced at the top by two cables. These cables prevent movement at the top of the column along the x-axis. The problem asks us to determine the largest force P that can be applied using a factor of safety for buckling of 3. Material properties are also given. We have the modulus elasticity, the yield stress, the area, and the moment's inertia. Begin this problem with our governing equation for all analysis and design problems. Actual is less than or equal to allowable. Now we must ask ourselves, actual what? Well, in this case, it is the actual load P, which must be less than or equal to our failure, since we're dealing with buckling, that will be the buckling load, divided by a factor of safety. Now in class, we learned how to calculate this critical buckling load, also known as the Euler load. You can find this equation on your RDC, so you don't have to memorize it. It's equal to pi squared times the modulus elasticity times the moment of inertia, divided by the effective length L prime. Now we can see that since we're given the geometry of the column and all of the material properties, we can conclude that this is an analysis problem. And the only property we don't know at this point is the effective length. So let's find the effective length, and we'll first start by looking at buckling about the YY weak axis. Now it's always best to find the effective length by beginning with a picture. So we'll begin with drawing our column of length L. We know that the column is fixed at its base, so we can draw in that support condition. Now the two cables at the top of the column are going to prevent the column from moving along the x-axis. Therefore, it is appropriate to model the top of this column as a pin connection. Now recall from lesson 33 that the effective length is defined as the distance between two successive inflection points, or points of zero moment. So we want to draw in the buckled shape for a pinned fixed column. Looking at this drawing, we see that we have a point of zero moment at the pin, and we also have an inflection point in this buckled shape located right here. Therefore, the effective length of this column is this distance I'm drawing right now. And if we look on our RDC for a pinned fixed column, the effective length is 0.7 times the original length of the column. We now have the information we need to calculate the critical buckling load about the weak axis of the column, which I'll call P critical sub Y. We can begin with writing our equation out once again. We're going to use the moment of inertia about the weak axis, or the y-axis, and we can start substituting values from the problem statement. We have the modulus elasticity is 70 gigapascals. Whenever I work with the SI system of units, it's helpful to convert things into newtons and meters. And since giga means 10 to the 9th, we have 70 times 10 to the 9th newtons per meter squared. The moment of inertia is 23.2 times 10 to the negative 6th meters to the 4th. And all of this will be divided by our effective length, which is equal to 0.7 times the original length of 5 meters, and this whole quantity is squared. If you enter these values into your calculator, you'll come up with a critical buckling load of about the y-axis of 1.308 times 10 to the 6th newtons. When we deal with loads in the SI system, we typically convert to kilonewtons, so we just need to divide by 1,000. We get 1,308 kilonewtons. That takes care of buckling about the y-axis, or the weak axis. We now need to look at the x-axis, or the strong axis. So it's time to draw another picture. Once we draw a picture, we can use this picture to determine the effective length for the end conditions when we consider buckling about the x-axis. I'll start by drawing a column of length L. We know that the base of the column is fixed, so we'll draw that support condition. And as we look at the column from this side, the cables are not going to restrain the column from moving along the y-axis. Therefore, we model the column as a fixed free column of length L. Now we want to draw in the buckled shape. Now going back to our definition of the effective length, there is a point of zero moment at the free end of the column, but I don't see any other inflection points on this diagram. However, if a mirror image of the column is visualized below the fixed end of the column, the effective length is this distance between points of zero moment. And if you look on your RDC, we see that the effective length for a fixed free column is 2 times the original length. Now we go back to our Euler buckling equation once again to calculate the load of the buckling load about the strong axis. We'll substitute in our values. We know pi. The modulus for elasticity is not going to change. It's still 70 times 10 to the 9th newtons per meter squared. And now we want to be careful to substitute in the moment of inertia value for the x-axis, which is given to us as 61.3 times 10 to the minus 6th meters to the 4th. And this is divided by the effective length. And our effective length is 2 times the original length of 5 meters. If we run these numbers on our calculator, we come up with a critical buckling load about the x-axis of 4.235 times 10 to the 5th, and the units are in newtons. However, it's more efficient or typically converted to kilonewtons, so we divide by 1,000 and we get 423.5 kilonewtons. Now if we compare critical buckling loads about the x-axis and the y-axis, we want to take the lower value. So we can determine that the critical buckling load is equal to 423.5 kilonewtons. And this value, and going back to our original equation that we used for analysis and design, we'll substitute this into our equation for the actual load, which our column can withstand. P actual is equal to the critical load divided by the factor of safety. So we enter in our values for the critical buckling load, 423.5 kilonewtons. We divide by our factor of safety, which is given us 3.0. And this will give us an actual load of 141 kilonewtons. But we're not done yet. There's one last check. We must ensure that the material is not going to fail before we reach our critical buckling load of 423.5 kilonewtons. To make this check, we will calculate the axial stress in the column under the action of this load, and then compare that stress to the yield stress of the material. Recall the equation for normal stress is simply force divided by area, and we'll use the critical buckling load divided by the cross-sectional area of the column, which is given to us. So we enter in 423.5 kilonewtons. Area of the column is given as 7.5 times 10 to the negative 3rd meters squared. And our critical buckling stress is equal to 5.647 times 10 to the 7th pascals. Now I did neglect one unit conversion. We have a mixed match of units, So we want to convert this kilonewtons into newtons. We do that by multiplying by 1,000. That will give us our answer in pascals. But whenever we deal with stress, we want to convert our units to megapascals if we're using the SI system of units. And we can do that by dividing by a factor of 10 to the 6th. When we make that conversion, we come up with a stress of 56.5 megapascals. We want to compare this to our yield stress of our material, and that is given as 215 megapascals. And since we are less than the yield stress, we can conclude that we will not have a material failure. Now I'll just summarize our final answer. The max load P that we can apply to this column with a factor of safety of 3.0 is 141 kilonewtons. If you're still confused on the topic of column buckling, I encourage you to schedule some one-on-one AI with your instructor. Thank you for listening today, and as always, remember, CE300 rocks. Rocks.